Okay, so first, I wanted to show you how you can use this idea of the Laplace transform, okay? How you can apply these tables in order to compute the Laplace transform of any function. So let's make this example. No? We have the function f of t that is equal to e elevated to the 4t plus 5, okay? And we want to transform this to the Laplace domain. So we can find f of s is equal to the Laplace transform of f of t that is equal to the Laplace transform of each function. Okay, we can apply the Laplace transform to the first term, okay, plus the Laplace transform of the second term. Okay, so here I am noticing that I am writing the s in these incursive letters in order to avoid confusion with the number 5. And with this representation, we can compute the Laplace transform. Okay. So in order to compute this Laplace transform, what we need to do is to, well, apply the Laplace transform to this term first. So the Laplace transform of e elevated to the 4t is equal, and we need to look at the tables. Okay, we need to find in the tables one function that looks very similar to this one. So if you go to the tables, there is one that is as follows. We have a function that is e elevated to the minus a times t, and we apply the Laplace transform of this, and this should be equal to 1 over s plus a. Okay, so based on this relationship, you can compare these two functions, and you can notice that, well, we have here two exponentials that are elevated by a constant times t. In this case, minus a should be equal to 4. Okay, we make a comparison between these two functions. So we can say that a should be equal to minus 4. Okay, so if we substitute the value of a here, you will obtain the following. 1 over s minus 4. Okay, here I am using cursive letter in order to avoid confusion with the number 5. And again, we can apply the Laplace transform to the second term. Okay. Here, what I recommend is that you factor always these numbers as follows. We can express this as 5 times 1. Okay. So the Laplace transform I can get out of the transformation the constant, in this case is the number 5. And if you look at the tables, we know that the Laplace transform of a constant with a value of 1, okay, the Laplace transform of this is 1 over s, okay? So we obtain the following. We have 5 times 1 over s, okay? So the result of this is equal to 1 over s minus 4 plus 5 over s, okay? And this is the result that we have, okay? So you need to follow the tables. With the tables, you can solve anything, okay? So I will make another example, okay? You can see that this is not too complicated to compute the Laplace transform. So we have another function that is f of t is equal to the cosine of 2 times t plus 7 times the sine of 2 times t. And we need to compute the Laplace transform of this. So the Laplace transform is equal to the Laplace transform of the cosine function, okay, plus I will get out of the transformation the constant, okay, and I will compute only the Laplace transform of the sine, okay. Here in the Laplace transform, you can get out of the transformation the constant, okay. You can remove that from the transformation, okay. You don't need to include that, okay. And now we need to look at the tables. For example, I need to look at the Laplace transform of a cosine function. The good thing is that for a cosine function of this form, the Laplace transform is equal to s divided by s squared plus omega squared. Okay, so if we apply the Laplace transform to this part using this expression, well, we need to identify the value of omega. Okay, so according to this, if we compare these two functions, you can see that omega should be equal to 2. Okay, so we can say that the Laplace transform of this cosine is equal to s divided by s squared plus omega squared, where in this case omega is equal to 2. So we have a 4. Okay, also we have here a sine wave. So again, we need to look at the tables and identify the Laplace transform of a sine wave. And this is equal, okay, to omega divided by s squared plus omega squared. Okay, and here you can see that omega for this function is equal to 2 again. So we can say that the Laplace transform of 7 times the Laplace transform of the sine of 2 times t is equal to 2 divided by s squared plus 4. Okay, and this is equal to s divided by s squared plus 4 plus 2 divided by s squared plus 4. Okay, but we need to multiply all of this by 7. So we have that f of s is equal to, well, I am using here to multiply also by 7. So we can get the following result. We have s divided by s squared plus 4 plus 14 divided by s squared plus 4. And this is the result. Okay. So this is some examples of how you can compute the Laplace transform. But it's a little bit complicated or a little bit more complicated to compute the inverse Laplace transform. So I would make an example of that. Only two examples, no, in order for you to see how the procedure is done. Um, so let's say that we have a function f of s that is equal to 2 divided by 3 times s elevated to the 4th power. Okay, here we have a function in the S domain, and we want to convert that into the time domain. We need to compute the inverse Laplace transform. But instead of computing the integral of the inverse Laplace transform, we can use the tables. So we want to compute the function f of t. Okay, so the first step that you can always do is to factor the constant values. So we can represent this function as 2 over 3 times 1 over s elevated to the 4th power. Okay? And with that information, we can look at the tables. Okay? So we have one table that, well, has more or less the following form. That is related to the Laplace transform of a function elevated to the n power. We know that the Laplace transform of this function is n factorial divided by s elevated to the n plus 1. Okay? Here you can see that this looks very similar. The problem is that we don't have the n factorial in the numerator. So what we can do is to multiply the numerator and the denominator by n factorial. But first we need to identify the value of n. So if we compare these two, you can see that n plus 1 should be equal to 4. So we can say that n is equal to 3. So now with this information, we can multiply 3 factorial in the numerator and in the denominator. So we have 2 over 3 times 1 over 3 factorial, okay? times 3 factorial over s elevated to the 4th power. Okay? So this is the expression that we want. And now you can see that this looks very similar. Now we can apply the inverse Laplace transform to this function, okay, to all of this. So we have here that f of t is equal to the inverse Laplace transform of 2 divided by 3 times 1 divided by 3 factorial times 3 factorial divided by s elevated to the 4th power. Okay? Now we can get out of the transformation the constants. Okay, so we have 2 divided by 3 times 3 factorial times the inverse Laplace transform of 3 factorial divided by s elevated to the 4th power. But I can express this 4th power as 3 plus 1. Okay? And if you compare these two, they looks very similar. In fact, we can compute inverse Laplace transform directly because we have mostly the same expressions. No, we have a factorial, okay? 3 factorial, that is the value of n. Also, we have s elevated to 3, that is the value of n plus 1. Okay, so we can apply the inverse Laplace transform directly. So we have 2 divided by 3 times 3 factorial, and this is equal, well, we need to multiply this by t elevated to the n power, that in this case is 3. Okay, so this is the result that we want. Okay, I will erase this in order to be clear about this. And well, that's it. Now we have all of this information. We can simplify this as follows. F of t is equal to, just a moment, this is equal to 1 over 9 times t elevated to the 3rd power. Okay, so that is the result. And well, we can make, for example, another case, okay, or only for completeness. What other exercise we can do? So we can solve the following exercise. We have the function f of s. I will write the s in cursive letter. So we have here f of s is equal to 3 times s plus 2 divided by s squared plus 25. And here you can see that we'll have a more complicated rational function in terms of s. So we can expand this as 3 times s divided by s squared plus 25 plus 2 divided by s squared plus 25. Okay, I only expanding this expression. Okay, now I can try to compute the Laplace transform as follows. We have the function f of t should be equal to the inverse Laplace transform of this term. I will get out the constant. So we have 3 times the inverse Laplace transform of s divided by s squared plus 25. Okay? And here we have, in this side, we have 2 times the inverse Laplace transform of 1 over s squared plus 25. And that's it. Now, we need to compute the time domain representation. So here we have, well, if you look into this term, okay, I will try to compute this term first. Okay, this one. This looks very similar, okay, to the Laplace transform of the cosine, no? We have that for a cosine function, omega t, the Laplace transform is equal to s divided by s squared plus 25. Okay, so, well, sorry, I placed here the 25. Well, in reality, this is omega squared. So if we compare these two, we can see that omega squared is equal to 25. Okay, so omega should be equal to 5. So we can compute the Laplace transform of this directly. Okay, so the Laplace transform of this term, no, if we substitute the value of omega here, we'll have 3 times the cosine of omega. Okay, that in this case is 5 times t. Okay, and for this term, well, this looks very similar to the Laplace transform of a sine wave. For a sine wave, remember that we have omega times t. The Laplace transform of this is omega divided by s squared plus omega squared. Okay? The problem here is that we don't have omega in this term. So what we can do, okay, in order to compute this Laplace transform, okay, I will place it here. You have 2 times the inverse Laplace transform of 1 over s squared plus 25. And I will multiply the numerator by omega, that according to my analysis, if we compare these two functions, omega should be equal to 5. So I can multiply the numerator by 5, okay, and also the denominator, that is 5, okay? But here I am getting out of the transformation this 5 in the denominator, okay? But if you compare these two functions, this one and this one, well, they are basically the same. So we can apply the inverse Laplace transform to this term directly, okay? So this should be equal to 2 times 5 times the sine of omega, that is 5 times t. So we can simplify the function as follows. We have 3 times the cosine of 5 times t plus 2 over 5 times the sine of 5 times t. Okay, so this is the result that we obtained. Okay. So this is the way in which you can perform this type of analysis. Okay, so this is for computing the inverse Laplace transform. But sometimes also we want to compute differential equations. Okay, so to compute differential equations, we can use the following relationships. So just let me one moment. We have here, what else? What else? I have prepared one example of this. Okay, here I have one. Okay, imagine that we have the following differential equation. Okay, so we have y prime plus y is equal to 3 times e elevated to the 2 times t. And for differential equations, we always have initial conditions, okay? Since here we have a first order differential equation, what you need to do, or what the problem needs to provide you is with the initial conditions. So here we have y times equals 0 should be equal to 4. Okay, we need the initial condition for y. Okay, because we have a first order differential equation. We need this initial condition in order to integrate the function. Okay, remember that when you're solving differential equations, you basically want to integrate the function. Okay, but here we have a very complicated differential equation. No? We have a non-homogeneous differential equations. We also have a forcing function in this side. So it's quite complicated to solve this differential equation by parts or by some other methods. So here we want to use the S-domain representation or the frequency domain representation in order to solve this differential equation algebraically. Okay, that is the main purpose of this. So if you want to compute this differential equation using the Laplace transform, you need to apply to all of the terms of this differential equation the Laplace transform. So we can do that. We have the Laplace transform of y prime, okay, plus the Laplace transform of y should be equal to the Laplace transform. I will get out the 3. So we have the Laplace transform of e elevated to the 2 times t, okay? And now we need to apply the Laplace transform of each term. So here we have a first order derivative for y. So the Laplace transform of a first order derivative is as follows. We just need to multiply s times y of s, okay? We are basically representing the function in the s domain where we need to multiply this by s minus the initial condition, okay? That is y at times equals 0, plus the Laplace transform of y, that is y of s, okay? And this should be equal to 3 times the Laplace transform of this exponential. And this is equal to 1 over s minus 2, okay? I am skipping the step of the table or the identity because I remember not this Laplace transform, but you can look at the tables and you can check for this. Okay, but you can believe me that this is the result. Now, we can substitute this 4 in the initial condition. So we have s times y of s minus 4 plus y of s that is equal to 3 divided by s minus 2. And we need to solve, now we have an algebraic equation, and we need to solve this algebraic equation for y of s. So we can do that as follows. We have 3 divided by s minus 2 plus 4. And in the left side, we will have y of s times s plus 1. Okay, and now we need to solve this equation for y of s. Okay, so we can move this thing to this side by dividing. So we will obtain 3 divided by s minus 2 times s plus 1 plus 4 divided by s plus 1. Okay? And what is? Well, we can compute the inverse Laplace transform. Okay? So we have here the inverse Laplace transform. Okay? And we have y of t is equal to well, here we have a problem, no? The problem is that we don't have any table that looks very similar to this one. So what you need to do is you need to express this, okay, this term that is very complicated, okay, that is 3 over s minus 2 times s plus 1. You need to expand this using the partial fraction expansion, okay? But since here, this is not an algebraic, this is not an algebra class in which you need to expand this as a divided by s minus 2 plus b divided by s plus 1. No? You need to make algebra to get the value of a and b. Okay, you need to make this partial fraction expansion. So you need to define a system of equations that in order to know what is the value of a and b that satisfy this relationship. Okay, but in order to avoid that waste of time, because this is one of the simple differential equations, but we can have second order differential equations. Okay, So instead of doing this, what you can do is to use your Texas and use a function that is called expand. And you can input this expression into the Texas in order to expand this function. And if you do that, you will notice that the value of A should be equal to 1 over S minus 2 plus the value of B. Sorry, this is a negative sign. Okay, so this is minus 1 divided by S plus 2. Okay, this is basically the partial fraction expansion of this term. Okay, so you can use this function in order to avoid this tedious algebra. Okay, because this is not the main goal of this course. The main goal is that you understand how you can solve the dynamics of a system. This is only a reminder of this topic. But you can use this function, no? For the exam or for some exercise in the homework. You can skip that step if you want to use this function. Okay, so we can say that y of s is equal to 1 over s minus 2 minus 1 divided by s plus 1, and we have this term 4 divided by s plus 1. And now we need to obtain the function in the time domain in order to solve the differential equation. So in order to obtain y of t, this is the inverse Laplace transform of y of s. And this will be equal to, well, we can compute directly here. This is basically the Laplace transform of an exponential. So we can compute the inverse Laplace transform as e elevated to 2 times t. Okay? This is the inverse Laplace transform of this term. Now we have here e elevated to minus t. And here we have we have 4 times e elevated to the minus 3 times t. Okay. And we have get the final result that is equal, well, we can simplify this further as 3 elevated to the minus e times t plus e elevated to the 2 times t. Okay, so this is the result of this differential equation. Okay, here you can skip this step. Okay, you don't need to perform this step by hand, this partial fraction expansion. Basically, this step only applies when you are solving for y of s. Okay, and then you need to apply the partial fraction expansion to all these terms in order to find the table that corresponds to the function in the time domain. Because the reason we are making this partial fraction expansion is that there is no function in the tables that satisfies this condition. Okay? So I will make another example of this topic. So we have here um, okay, this is another example, just 1 minute. We have the following differential equation. We have y double prime plus y prime is equal to 5 times the cosine of 2 times t. Okay? And we have a second order differential equation. So you need to have two initial conditions. One for y at time equals 0, that in this case, this is equal to 0, and another initial condition for the first derivative. Okay, that also is 0. Okay? Again, here we have two initial conditions, one for y and another one for the first derivative, because we have a second order differential equation. Okay, basically this means what is the, for example, this function can describe the velocity, the position and acceleration of a particle. Okay, so here we need to have initial conditions for the position or for the velocity in order to compute, for example, the acceleration. We want to solve the differential equation or this second order differential equation. Okay, that has some input, uh, some forcing function in the right side. Okay, so we can apply the Laplace transform to all of the terms we have here. The Laplace transform of y double prime, okay, plus the Laplace transform of y prime, and this is equal to 5 times the Laplace transform of the cosine of 2 times t. Okay, now we can apply the Laplace transform to this term. So we have s squared, okay, times y of s. Okay, here we are using this relationship because we have a second order differential equation. So when you have a second order differential equation, you have s squared times y of s minus, okay, just one moment. We have minus here, minus um, the minus s times the initial condition of the function y minus the initial condition of the first derivative, okay? Plus, okay, we have here a first order different derivative, so the Laplace transform is s times y of s minus the initial condition of y, okay? And this is equal to 5 times the Laplace transform of this. But we know that the Laplace transform of a cosine function is s divided by s squared plus omega squared, that in this case omega is equal to 2, so we have a 4. And here we know that these values are equal to 0, no? We can remove this, we have removed this, and also this, and you will obtain the following. You will have s squared plus s, that is equal to 5 times s divided by s squared plus 4. And this is all multiplied by y of s. Okay. Now, what else we can do? Well, we can solve this algebraic equation for y of s, and this is equal to 5 times s divided by s squared plus 4 times s squared plus s. No, this is the solution of the algebraic equation. Well, again, you have this very complicated term, okay? So you can introduce this in your textbooks with the function that is called expand. Okay, you introduce all of this into this function, and we can express y of s as follows. We will have here the following. We have mm, minus s divided by s squared plus 4 plus 1 over s squared plus 4 plus 1 over s plus 1. Okay? And, well, if we apply the inverse of the transform to this y of s function, we can obtain y of t. So we have this term, and this term looks very similar to the Laplace transform of a cosine. So if you look at the tables, you can see that this is equal to the minus cosine of omega. Here omega, based on this, is equal to 2. Okay? So you can, if you look at the tables, you can see that this looks very similar to the Laplace transform of a cosine. Also, we have here, well, here we have a problem, no, in this term. And this looks very similar to the Laplace transform of a sine wave. But we are missing the omega in the numerator. So what you can do is to multiply and divide this term by 2, divided by 2, and multiplied it by 2, no? And here, well, you can see, you analyze this, that omega is equal to 2, okay? Because this looks very similar to the Laplace transform of a sine wave. And if you inverse that, you will obtain that the inverse Laplace transform is 1 over 2 times the sine of 2 times t, okay? And this one looks very similar to the Laplace transform of an exponential. So here we have e elevated to the minus a times t. But here a is equal to 1. So I can express this as follows, 1. Okay? And this is the final result. Okay? So these are some examples of how you can use the Laplace transform to solve to transform functions by either using the Laplace transform or the inverse Laplace transform. But the crucial thing, at least in this course, is that we want to use this Laplace transform to solve differential equations, because if we solve the differential equations, we can understand what are the dynamic behavior of any system, either mechanical, electrical, thermal systems, hydraulic systems. We can analyze all of them using this representation. Okay? So that's all for me. I hope you like this video and see you later.